Hello and welcome back to the video series of finite element analysis. I'm Bhavik Soneji and today I'm going to talk about the consistent and the lump mass matrix. So let's get started. So in the previous video we have derived the equation of motion for the axial vibration of a rod and beam. So let's understand what is consistent and lump mass matrix today. So this is the axial rod and for this axial rod we have derived the equation of motion for vibration. So this is my governing equation. So now let's understand this governing equation, what it means. So the first term indicates the stiffness matrix, which can be written as K, capital K. This displacement matrix can be written as displacement vector. Then this matrix is representing the force element, which can be represented by P, plus this third term. Here omega is the natural frequency, so this whole portion can be written as mass, and omega is my natural frequency, u is my displacement vector. So this is the governing equation or equation of motion. So let's understand first thing first. This is my stiffness matrix. Force and mass. Omega is my natural frequency of vibration. And u is the displacement. So if we are representing the free vibration, then this whole term becomes zero because there is no external force is required. So it could be written as K u is equal to m omega square into u. So this is the equation of free vibration. Because there is no external force is required, so this component of external force becomes zero. Now second thing, here you can see mass. So first let's understand, for mass, this mass matrix is represented as m equal to rho into a into l divided by 6 and some matrix value. So as all of you know that density is the mass divided by the volume. So volume is nothing but A into L, area into length. So if the 3D object is like this, then L is my length, A is my cross section area, and volume is A into L, area into length. So that is my volume. So mass is represented by m is equal to rho into A into L. So that's why this whole equation is known as mass matrix. So now let's understand, we have two options for considering the mass matrix. First is consistent mass matrix, which is also written as CMM. And second option we have is lump mass matrix, which is also written as LMM. So first let's understand what is the difference. So in this equation, in this mass matrix, if our matrix is derived by the shape function, then we can have the consistent mass matrix. Second thing, if we consider the element, the 1D element, so throughout the element, the mass is assumed as a uniformly divided. So throughout the element, this is my element which has two nodes 1 and 2, and on this element my mass is throughout same, so it is uniform throughout my element. So that's why it is consistent mass throughout the element, that's why it is known as consistent mass matrix. And let's see for the lump mass matrix. This lump mass matrix, the mass is not divided or distributed same, but suppose total mass of this element is m, which is rho a l. So total mass is rho a l. So we need to assume that on the element number 1, the mass m1 is equal to rho a l by 2, and on this second element mass m2 rho a l by 2. Because what we do, total m is equal to m1 plus m2. We are dividing the whole mass and we lumped this mass on one element and second element. So if number of nodes are more, for example we have 3 nodes 1 2 3, so instead of uh, m1 plus m2 it will be m1 plus m2 plus m3, and it can be converted by rho al by 3, rho al by 3, and m3 also rho al by 3. So that is this is the difference between the consistent mass matrix and lump mass matrix. So now let's understand the uh, equation for consistent mass matrix. So now let's derive the equation for the consistent mass matrix. So first of all, let's consider a element which is having two nodes, node number 1 and node number 2. Here the x is equal to 0, here the x is equal to L. Total length is L. So now the mass matrix is defined as the integration over 0 to L, because the total length is capital L, into rho into shape function, transpose of shape function into shape function to dv over volume. So shape function, first let's define what is shape function here. So shape function is 1 minus x by L and x by L. Now if we do the transpose of this thing, the row will be converted into column. So 1 minus x by l and x by l. So putting these two values, first and second, into our equation, mass matrix will be 0 to L, row is common, 0 to L. Instead of dV, we write dx into area A. First matrix is written here column wise, 1 minus x by L divided by x by L into 1 minus x by L, x by L. So here we have the equation. We can rewrite this equation if we do the multiplication of these two matrices and taking the area common, which is constant. So integration over 0 to L, rho into A common. If we do the multiplication, it will be 1 minus x by L whole square, x by L, 1 minus x by L, x by L, 1 minus x by L, x square divided by L square into dx. So now if we do the integration, we can have the equation of mass matrix is equal to 0 rho into A, and the matrix is now integrated over 0 to L. So first is L by 3, second L by 6, L by 6 and L by 3. So now if I am taking the L by 6 common from this matrix, so rho into A into L divided by 6, we have 2 into 1, 2, 1, 1, 2. So this is my CMM, consistent mass matrix, and that's how it is derived. So let's see now, whatever we have derived is same as our previous equation. So here you can see my consistent mass matrix. It is same as the mass matrix we have derived. So from shape function we have derived by putting the shape function values, we have derived the equation of CMM. So hope you find it useful, and thank you.